Hey, John here. In order to understand the non-blocking assignment, we have to fully understand this stratified event queue. A big thanks to all of you that like, subscribe, and our Patreons, especially the VIPs seen here, that go above and beyond to support the channel. Thank you very much. First, let me make it very clear that the stratified event queue is only something that applies to simulation of Verilog code. Okay, so this is how we are going to test and debug our code. When it comes to synthesis, it's a different story. We'll get more into the details of that later on. It turns out there's less to do with synthesis. The problem with simulation, as I've mentioned before, is that you generally have fewer CPU cores to do things than you do transistors and LUTs in an FPGA. So you're forced to simulate what it looks like to make everything happen at once, okay? So here's how this works. When Verilog is running, it has this notion of work to do, all right? And it gets slotted into these 5 different stratifications of one big queue. I think of these as lists, okay? The active list represents all the things, all the events, all the work that you need to do right now in what the specification for Verilog calls a simulation cycle. Those might be the sequence of assignments that you see in an initial block that initialize a bunch of variables and things like that. The inactive list is the items that were in the active list but have a #0 in there. We talked about this before. That's a way to say, let me continue now, but after everything else that's already scheduled, I should say, to run now has completed. So this is where you put things that say, move me to the end of the list, but still run me before the simulated clock advances. That's this list here. Non-blocking list is the list of the assignments that we're going to talk about in a minute. We'll come back here in a minute. The monitor list is where the monitor and strobe commands go. So if I say I want to monitor something, or we talked about this before, the monitor and strobe, those represent a time in the simulation after which all the variables will have been updated and assigned values before the clock ticks into the future. So we can print out a variable after all of the code in an always block and all the always blocks have completed and is stable. Okay, so that's why those are scheduled down here, because we want to finish doing what we want to do right now. And that's what happens in these 3 lists here. This all represents work that has to be done before the clock advances into the future time, which leaves us with the future. Down here, if you say #5 or something like that, you're saying wait 5 clock ticks and then do something. Well, when that happens, you encounter that. What all you do is you take the list of work that needs to be done, you move it down here into the future list and say wait 5 ticks before this is done. Thank you very much. And then you go back and finish running anything else in the active list that's still there, along with all the inactive stuff. And keep in mind that processing stuff in the active list and the inactive list can in itself create more events, more work in the active list and more inactive things and so on that are all still in need of running before the clock moves forward, right? I mean, every time you assign a value to a variable, you're probably creating something else that needs to be done in this active list, right? I mean, think about it. You update a variable, there's probably an always block somewhere that needs that variable as its input. And if you have always star, which we talked about before, that means that always blocks will need to run as a result of that variable being updated. So that is how things get into this active list, and we already know how things get into this inactive list. The non-blocking list is quite simple. You simply assign a value to a variable using the non-blocking assignment operator. That's how things get into here. The fact that it's down here after all this stuff means that when an assignment is done, it will happen after everything else that can run now, and all the side effects that are created and more work that has to happen as a result of things that are being updated now have completed. It's only after all this stuff is done and anything that it also creates, all the other events that are created as a result of doing work in here, when this is fully depleted, then you move on and say, okay, I can update some variables now. Now keep in mind, updating these variables will also quite likely create more stuff to do in the active list and the inactive, not necessarily the inactive, because you don't usually put #0 in a non-blocking operator. I'm not even sure it's legal. But my point is, if you're going to update a variable, you're probably going to be putting something in the active list, okay? At which point, after the non-blocking stuff is done, you're going to go back and do more active stuff. Anyway, it is after the non-blocking stuff is done that we move on to the monitors and strobes. We already know that these are done after all the other work that could be done now has completed, right? And when that happens and there's nothing else in these lists, there's literally nothing else to do now, and we move on to the future. Okay? I had a note down here that says, by the way, notice that if the future queue ever drains, future list here, right? Then there's nothing to do, and that's one way to terminate a simulation. Let's look at some code here. This is in the repo that is linked to below here and in the description below the video on YouTube. So let's see, what's this first example? Let's demonstrate some edge-sensitive always blocks. Now, we haven't seen these yet. Let's have a close look. See, very simple example. What do? We save some stuff into the file. We have a reg called clock. The clock starts out as 0. It goes 1, 0, 1, 0, 1, 0, 1, 0. And then we wait a little while and we stop. Okay? That's all we're going to do here. Now, look at these always blocks. Got 3 of them. This one has a sensitivity list that says if anything that is used as an input in here changes in any way, run this code, okay? So what is its input? Basically, it only has the clock. Time is a special case. It doesn't count. No pun intended. It does not count in this sensitivity list. Otherwise, it would be running constantly because the time is always changing, right? What's this one? Pos edge and neg edge. Now, because I said star here, I could have just as easily said clock, I suppose, because that's the only input to this always block, right? Just to make these all kind of match, right? So this one means if clock changes in any way, in other words, if it goes from a 0 to 1, or if it goes from a 1 to a 0, execute this process. This one says if it changes from a 0 to a 1, execute this process. But don't execute it if it goes from a 1 to a 0. This one says if it goes from a 1 to a 0, execute this process, otherwise don't do it at all. So this is if it changes in either way, only in the positive going edge, only in the negative going edge. So if we run this, we can see what's going on. The star goes at time 0, presumably because it was assigned as 0, and it transitioned from X to 0. This one here went from a 0 to a 1, and it triggered the star. And it also triggered the positive going edge, always block at the same time, okay? Then down here we have the negative going edge, right? It went from a 1 to a 0, and then it went from a 0 to a 1, and so on. So hopefully this makes sense. It's pretty straightforward, right? Don't worry, it'll get complicated. All right, what do we got here? The quintessential example. I got a problem with this example because this is the one that everyone everywhere uses. And therefore, I can't tell whether the person knows what they're talking about or they're just copying everyone else. I went back and forth on whether I was even going to put this in my example, but I decided to do it because everyone has seen it. And if you're just getting started, I'm doing you a great disservice by not introducing this to you, okay? So you need to know this, but my concern is Not that it's what everyone's doing. That's just part of it. The other part of it is it's such a simplistic thing. It's almost a trick, and it could result in you misunderstanding or building a false image in your head. I don't want to rant too much about it. We need to take this further, is my point, than this trivial special example here. But let's look and see what's going on. We have our clock. And it's going to go, whatever, 10, 10, 10, 10, 10 over the course of time. We have two reg variables, A and B. We do the usual thing, open up our stuff, dump it to a file. We've got a monitor on A and B. We assign A an 18. We assign B a 0. Clock starts at a 0. We wait a little while, and then we finish. Okay. What's this? Okay, this is your non-blocking assignment. And this will swap the values of A and B. All right? How often do you really need to do that? I would argue probably never. But, it's true, and this is an example of how you use non-blocking assignments, but it's not a practical use, and it doesn't drive home, in my opinion, what's really driving the need for these non-blocking assignments in simulation. So let's start with the simple thing here and observe that because we use a non-blocking assignment, rather than simply taking the value in this side of this expression, which is trivial right now, it's just the value in A, which up here we signed it 18. So what is this really doing? If this was any other code, right? Let's first look at what we already probably know from other languages. If I say B equals A here, what I'm going to do is take this 18 and copy it into B. So now B is 18 and A is 18. Down here, I'm going to take that 18 and put it back into A. This line of code down here has no beneficial side effect whatsoever. Okay? Written like this. That's what it means in Verilog. That's what it means in other languages as well. Oddly enough, we'll play around with this some more later on in synthesis. It turns out that whether you do this or this, you get the same results when it really comes to synthesis. But I don't want to digress too much. Let's stay focused on simulation here. That's why they're here. In this mode, remember what it means. We come over here and we evaluate what's over here now when we encounter it as the positive edge of clock transitions, okay? So it means we go and get the value in A. We don't put it into B now. We make a note that we want to put 18 here into B, and we put the assignment part of this statement here into the non-blocking list in our stratified queue. Then down here, we evaluate this side of this expression, no matter how complicated it is. In this case, it's trivial. It means go get the value out of B, which is currently a 0, okay? Put it on a note, put it in the non-blocking assignment queue, and remember that later on, we need to put that 0 into the A variable. We then run to the always block, we stop running. Because we're in the stratified queue, we look around. Do we need to do anything else right now? Maybe we do, maybe we don't. Depends on the rest of your application. Here's a continuous assignment down here that says assign sum equals B plus 1. B has not changed yet. Therefore, there's nothing to do here. Okay? I mean, you could argue that during initialization in time step 0 that, maybe it has to do it once to get things going. That's fine. But by the time there's a positive edge on the clock, at this point, B is not changed. Therefore, this is not going to do anything. This is not in the active queue. This isn't even in the future queue. It's nowhere right now. Okay? All we have are these two little notes in our non-blocking list of things to do. So we're fully drained in our active list. We haven't put anything in our inactive list. We have this in the future list. Okay? And therefore we move on to the non-blocking list. And what do? We update the values in B and A at this time. with the values that we got earlier when we evaluated these expressions over here. This is why this actually swaps the values of A and B. And as a side note, because B is now changing, this thing over here needs to be processed, and this operation will be put into the active queue. Then the active queue will be processed, and the sum will be updated. At this point, there will be nothing in the active queue. There won't be anything in the inactive queue or the non-blocking queue. Any monitors up here will be fired off. At that time, we'll print out this stuff. In fact, we should go ahead and put the sum in there as well. Sum. And I think this will work. Okay, there we go. And we can see what happens here. We got sum is 119, 119 at time 0. Now, let's see what we got here. What if we start? A was 18 and B was 0, right? So at time 0, and that makes sense. A was 18 and B was 0. So that's what we got. And the sum is currently 1 because 0 plus 1 is 1. At time 1, we see the clock go from 0 to 1 because it started as 0. This might actually work better if we plot it, because then we can see it over the course of time. That's why we have kind of both of these going on in these examples. You can look at it and think about it however you want. Some of these work better, in my opinion, on a time series like this. Okay, so what happens here? We start out with a 12 and a 0 at time 0, right? And the clock goes from 0 to a 1. We see the positive going edge. We swap the values of A and B because they went through our non-blocking queue. If they don't go through that non-blocking queue and defer the final assignment to the A and the B values, then it won't really swap them, will it? It might, if we update B too soon, then all we're really doing is storing the value from A back into A, like I said before, okay? So that's why this works. It's because of this non-blocking stratification in the queue. Now, this trivial little example is interesting, but not representative of the reason that they put this in here. I mean, on the one hand, it's sort of like, oh, yay, it saved me a line of code. I don't have to have a temporary variable. I mean, no, you don't change an entire language so you can do something cute like this, all right? Do not memorize that that's what this is for. I think you're just, that's a waste of your time. You have to look at it in a bigger picture here. This non-blocking queue, variations, okay, I didn't put much to say here. This non-blocking queue is really used for more sophisticated things. This looks deceptively simple, but there's a little more going on in here. And it's increasingly representative of why we have these non-blocking operations. Notice I've got separate always blocks here. They're not in all one big one, because that's another issue, right? I mean, let's go back to the previous example real quick. In here, these are in the same always block. We could have put them in separate always blocks and put an N down here. This probably would be a better example now that I think about it. And the reason I say this is because once you do this, there's no guarantee as to what order these are going to be done in during simulation. In synthesis, it all happens at the same time anyway, because as we will see, this positive edge-going clock is the clock input on an actual latch inside the FPGA. And all of the latches, in this case two of them, the B and the A latch, both have the same clock hooked up to their inputs, and therefore both latches trigger at the same exact time. And that's why this actually would work in synthesis. And why synthesis, by the way, doesn't even care that it's a non-blocking operation in simulation. Because in synthesis, the gates are edge-triggered and they all fire at the exact same time. Okay? Therefore, there's none of this racing or order of operations that you have to concern yourself with, like you do in here, right? What if this one goes first and then that one? Or what if that one goes first and then this one? That's what happens in simulation. And if you use an assignment like this, Even if you have like a temporary value, if I say like temp equals B, like you would in a C program, and then down here you say A equals temp, well, if they're separate like this, and this one down here goes first, it won't work at all. If it's all in one big wad, this would work, right? Oops, that's not quite right either. In another language or whatever, when you're doing this procedural, orderly sequence of events or of instructions here, right? So, I mean, in this case, it's so obvious that that's the way to work around it. And like I said, you don't ruin a language to get rid of a temporary variable. That's not why that's there, okay? It's there because you can't tell the order in which these things are going to happen. And while I could put this in one big always block like the other one was, or I could break it up into pieces, the one big always block is in maybe a temp variable or something like that, might solve my problem. But my point in beating this up is that when you have a real software project with thousands, tens of thousands, hundreds of thousands of lines of Verilog, it's not going to all be in one always block. It's going to be in many always blocks, in many different modules and different files. And when you compile this stuff all together, they're going to be all over the place. And at that point in time, I absolutely guarantee you're not going to be able to keep it straight what happens in what order. Especially because the simulators themselves don't guarantee anything. It turns out, I'm running this on Icarus. That's the one that I'm using. It turns out that in Icarus, if I have 4 always blocks in one module, which I do right here, okay, and all of them end up in the active list of my stratified queue all at the same time, they will get done in this order, okay? But that doesn't necessarily mean that they have to run in this order, especially if there's more than one line of code inside these always blocks. Trust me, order is not going to be maintained. You go to a different simulator, it may do something different. You put this in a different module, is that module going to run its always block first? I don't know. That's why we need this deferred updates that are going on with these non-blocking assignments, okay? So let's look and see what's going on here. You say Q equals A plus B. That's fine. And we also mess around with A and we mess around with B while this is running. So if I do this first, the value of Q would be very different than if I do this first, right? Now, what if I do this? Then I guess the order in which these two are done don't really matter because this is fully self-contained, that's fully self-contained, and this one here depends on these other two, okay? This is where it gets interesting. If this one happens to run first, remember, it's going to calculate A plus 1, and it's going to put it in that non-blocking, this deferred assignment that's going to take place after everybody else that can run now are done. So I'm going to take A plus 1. A is currently 0. I'm going to add 1 to it, and I'm going to remember, I got to put a 1 in an A, but not until everybody else that needs to run right now has finished. And maybe this one will run. I need to put a 1, in this case, into B. I got to remember that, but don't do it right now. I have to calculate A plus B. I can do that. 0 plus 0 is 0. Oh, but I got to remember to put that into Q later on. Okay? It is only after all the right-hand side of each one of these expressions are fully evaluated, those values are salted away in the non-blocking assignment queue, then we go off and do this non-blocking assignment updates over here. And that's why this will always add 1. This one here will add 1. And Q, think about this now. Q is going to be the sum of what A and B were before this clock rises. So the first time all these run, the first time there's a rising edge on clock, Q is going to be 0. Because A is 0, B is 0, 0 plus 0 is 0. That's going to get put into Q. And at the exact same time that gets assigned a 0, A is going to be 0 plus 1. That's a 1, and that'll be put into A. B will be 0 plus 1. It'll be put into B. So we're going to have a 1 here, a 1 here, and Q will equal 0. That's just the code that I wrote, okay? This can be hard to keep in your head, all right? Q does not equal A plus B now. Q equals A plus B of what it was before this clock went up, all right? So let's go ahead and do a make plot on this and watch what happens over the course of time. Okay, let's see here. Put all these on the screen. Let's zoom to fit. Okay, what's Q down here? Q is garbage. It's unknown, because we never initialized Q. We initialized A and B, but we never initialized Q. The clock goes down, and then it goes up here. So there's our positive edge. And we have 1 and 1 go into A and B, because that's A plus 1, B plus 1. And A plus B is 0 plus 0, and we end up with 0 over here in Q. All right, so this looks like it's wrong, but all of these, this is 0 plus 1 is 1, 0 plus 1 is 1, and 0 plus 0 is 0. Now we have 1 plus 1 is 2, 1 plus 1 is 2, and 1 plus 1 is 2. All right, 2 plus 1 is 3, 3, 2 plus 2 is 4. All right, now this is a little bit more interesting example, and it forces you to get your mind around a few more things, which I think is a good thing to stick in your mind right now, so you don't accidentally oversimplify the impression that you have of what this really means. Okay, I beg of you to stay in kind of an academic view of this for the time being, and think of the stratified queue and the fact that this assignment is deferred until everyone's right-hand side of all these expressions are done. They're all waiting on pause edge of clock. Therefore, they're all in the active list at the same time in whatever order the simulator decides to put them. Now, it may very well be, I'd have to recheck the actual specification of Verilog, to that, I don't know, okay? Feel free to put a comment below. Some of you guys are pretty smart. Throw in some comments. I don't believe that the specification says that each of these always blocks will run in the order that they appear in this module if all 3 of these always blocks do appear in the same module. I do not know that that's an official rule. It turns out that I can say this one starts before this one starts, before this one starts, when we're running on Icarus, okay? Because if you play around with this program, and I encourage you to do so by running it like this, okay? Oh, we don't need these. Yes, you do. Now order matters a lot, okay? If you run this, look what happens to these values. We got 0 and 0 and A and B, and then you go down here, Q is becomes 2. Remember, before it was 0 on the first rising edge. Okay? Now, the second rising edge, these both 2, and this is 2. So this is a very strange, this is really weird. I expected it to be somewhat consistent, as it looks like it's taking 1 plus 1 to get 2. Well, obviously it did, right? Now it's taking, I don't know what to get to. It must be still, now it must take it the old values and get 2. Now it's taking the new current values of 3 and 3 to get the 6. And down here it must get the old 3 and 3 to get 6. This is like inconsistent even in the same simulator. Okay? All right, this is really not making a lot of sense, okay? That's why when we're in simulation, you want to defer these assignments. And this is what I really wanted to drive home. Because when all these always blocks are in different modules and stuff, you don't know how complicated this expression is, and you don't necessarily know what inputs they're even using. Even if they're not using the same inputs that you are, they might be using something like that is still derived indirectly from some input that you are, and that might not be calculated in the simulation until later. So the order of operations is absolutely critically important because the simulation is fake. And we need to make sure that all the pos edge expressions are all calculated using the input values that existed at the point in time 0, seconds prior to that positive edge. Okay? So that everyone has the same chance looking at the values before someone else stomps on it. This guy stomps on A before that guy. You don't want that. No. Okay, you want to make sure everybody has a chance to read their inputs before the anybody or anybody else has a chance to change it. That's why we have this special deferred non-blocking assignment. It is really what you have to take away from this, all right? It's not about swapping the value into registers. Yes, you can do that as a side effect. And yes, you cannot do that if you don't have deferred non-blocking assignments. But in order to understand the non-blocking assignment, I beg of you to keep the stratified queue in mind, okay? During simulation, this is absolutely critical. It's the rule of the land, all right? Now, later on, we'll play some games. We'll actually run some of this code on an FPGA, and we will see that the FPGA doesn't care whether you're using blocking or non-blocking assignments. Okay? So all this really is, just like I said at the beginning, all about simulation. The reason the FPGAs, this synthesis, does not care about non-blocking assignments is because the FPGA does do everything at the same time. So while an assignment is done to A, at the same time on the same clock, because it's not jumping around with a bunch of different threads on different CPU cores, they're all being done at once, the queue can get assigned at the same time, all right? That's just what you get when you have a bunch of latches that are edge sensitive, all right? But you can't really do that with simulation, and it becomes inefficient if the simulator has to figure out how to do it on its own. So you have to help it, okay? And if you don't do this right, you end up with a simulation that doesn't behave in the same way that the FPGA will do in synthesis. Now, as we move along, we will see there are some simple rules, techniques that say if you use these non-blocking assignments in a certain way and you're consistent, it doesn't have to be difficult on you to kind of remember, should I use a non-blocking one here and a blocking assignment there, and you strew these all over the place. And yeah, you could do that, but that's a mess, and no one wants to see that. Don't ever give me your code if you're going to write it that way. No one wants it. I'll show you some techniques that are real simple. Some people don't like them because they can be a little bit verbose in the code-wise, but in reality, it's pretty straightforward, and once you get used to it, it's nice and simple, and anybody will be able to read and understand your code. It's the nice way to do this, okay? You can't screw it up if you follow some simple rules. If you think you're better and you want to break the rules, knock yourself out, but be careful what dangers lurk out there, and you may also find it that you're going to have trouble if you ask somebody to help you, because they just won't be able to untwist it. I mean, if you can't untwist it, why should I be able to untwist it? Don't ask me to help you with your code if you write a mess. I mean, nobody wants that, right? So I'll save that for next time. We'll see a lot of non-blocking and blocking assignments and a lot of edge-sensitive always blocks as we build state machines that have, like a UART or an SPI driver and things like that. These are all based on clocks and which is it a positive edge or a negative edge and all that fun stuff. So those kind of devices are fairly straightforward, relatively speaking, and great fodder for playing around with stuff like this. So if you want to work ahead, Google around and see if you can find some UART Verilog code floating around the internet, or maybe an SPI driver or something, and see what you can find out. We'll dive into that next time right here in John's Basement. Thanks for watching. We'll see you then.